the question 16, part B, which is the last question you will get in your full unit HSC exam. All we have is an integration, but it's in, right? It's the recursive integrations which we get. In is equal to integrate 0 pi on 2 sine 2n plus 1 2 theta and d theta, and n is equal to 0 and 1. Prove that in is equal to 2n and 2n plus 1, in minus 1, n is greater than 0. Okay, so it's just it's just integration, right? We did this, I think you guys probably did it a million of times now. But what you do have to notice is how we integrate. So with the skills, I'll use the Zoom to annotate, okay? So part 1, I'm going to drop down part 1. I'm going to copy part 1 because I don't have enough space down the bottom. So I'll do it on Zoom and I'll clear the board. Okay, so in is equal to 2n over 2n plus 1 and in minus 1. Let's see. Yep. All right, so I'll be annotating using the Zoom annotate. All right, essentially I have my in equals to integrate 0 pi on 2 sine 2n plus 1 2 theta times, is it theta or x? Okay, yep, theta. So times d theta, okay? When you're gonna have to do this, usually your recursive integrations, what we have to do is by part. By part is the only way to do it. So I'm gonna let you. Which one I'm gonna do here? I'm gonna let u equals to 2n, okay, sine 2 power of 2n, 2 theta, and du equals to 2n sine 2n minus 1, 2 theta. And don't forget your trigonometries, your trigs follow your chain rule. So what we get is differentiate sign. You also get cos 2 theta. Okay, it's 2 cos 2 theta. Okay. Now let dv equals to sine the single one, right? So I have 2n plus 1. So now I'm going to let the single one. So not 2n. Let dv equals my single sine 2 theta times d theta. I will get my v as my half cos and negative, half negative cos 2 theta. Okay, maybe I'll write negative cos 2 theta on 2. Okay. Now last thing is my in is going to fill in with the uv, the formula minus integrate v times du. What we get is sine 2n 2 theta times the negative cos 2 theta on 2. Remember you're 0 on pi on 2. Okay, it is definite. This is, sorry, right? Minus 0 on pi on 2 over here as well. We have our v, which is negative cos 2 theta on 2 times by my du. So over here, sorry, I forgot the d theta. So we get 2n sine 2n minus 1, 2 theta, and then also times by 2 cos 2 theta times d theta. All right, the first part, if you're gonna sub it in, right? The first part, if you sub pi on 2 in, because this is two things times together, I sub pi on 2 in, and then I get sine 2 times pi on 2. The 2 on the top and bottom cancel out, you get sine pi, right? Which returns you 0. And then minus your sine 0. Again, 2 times 0 is still 0, so your sine 0 still returns you 0. So you just get 0 minus 0 in your UV part. Now in the second part, I'm going to take the negative out, so I get a positive. So I get a positive, and now I'm going to take the 2n out, so I get 2n, integrate 0 pi on 2. The bottom 2 and this 2 will cancel out, so cross and cross. So what I get is cos 2 theta sine, erase this, get sine 2n minus 1 2 theta, and then times by cos 2 theta again, times d theta. So what I get is 2n integrate 0 pi on 2 cos squared 2 theta sine 2n minus 1 2 theta times d theta. Okay. Now, very simple. I'll write on the top left using the cos theta, cos squared theta plus sine squared theta equals to 1. Trig identity, what I get is cos squared theta is equal to 1 minus sine squared theta, right? So what I will get here is 2n integrate 0 pi on 2 cos squared 2 theta. Exchanging your cos squared now. So I get 1 minus sine squared theta 2 theta, okay? The theta is 2 theta, remember? And then sine 2n minus 1 2 theta times d theta. Expanding, what we will get is equals to 2n integrate 0 pi on 2 sine 2n minus 1 minus sine 2n. Now, 2n minus 2 plus this 2, okay? So that will give me plus 1, 2 theta times d theta. Splitting it, this will give me 2n integrate 0 pi on 2 sine 2n minus 1 times d theta. And then minus my 2n integrate 0 pi on 2 sine 2n plus 1 d theta. There we go. Okay. Now you will realize this is your 2n minus 1 plus 1, and this is your 2n plus 1. Okay? So this means putting our left-hand side in, I have in equals to 2n in minus 2n, to in minus 1 and 2n in. Rearranging, right? So let me write the I better because I can't write alphabet letters right now. Okay, shift the in onto the left-hand side, I get 2n plus 1. In is equal to 2n in minus 1. And finally, I just get my in equals to 2n over 2n plus 1 in minus 1. And that is my part I proved. Okay, so now for part 2, what it says, deduce that in is equal to 2 to the power of 2n n factorial and to the power of 2 over 2n plus 1 factorial. Okay, so let me just write part 2 down so I get more space for this. So part 2 is asking for in, deducing that is equals to 2 to the power of 2n. Okay. And what did it say? 2n factorial squared over 2n plus 1 factorial. Yep. Okay, so I'll just keep it like this so I get more space. All right. Now I get in. I know my initial formula of in. Well, I need to use my part 1. So let me scroll a bit. Scroll backwards a bit. Okay. Don't need to use that. Okay. Right. So I know my in is equal to 2n plus 1 of in minus 1. Then hence my in minus 1 will be subbing in the n minus 1. So 2n minus 1 over 2n minus 1 plus 1. What I get is 2n minus 2 over 2n minus 2 plus 1. So 2n plus 1 in minus 2, dropping one more. Okay, and this will go on. So your in minus 2 will equal to 2n minus 4 over 2n. Oh, sorry, minus 1 over here. I was getting confused. I was like, how come it's the same thing? All right, so minus 3, in minus 2. This is what we will get. And as it continues onwards and onwards and onwards, we'll get this onwards and onwards and onwards. So let's try to replace the in minus 1 with this and try to replace the in minus 2 with this and everything inside. What you will find is your in will be equal to 2n over 2n plus 1 times by your 2n minus 2, 2n minus 1, times in your 2n minus 4, over 2n minus 3, 2n minus 6 over 2n minus 5. And this goes on and on. You will realize the top is always minusing an even number and the bottom is always minusing an odd number until what you should get is, because you're minusing a digit, you're minusing 6 on top of 5, right? 4 on top of 3. What you will get is a number less, an even number that's 1 digit less than your 1 digit less than your denominator, yeah, than your odd number. Okay, and then lastly, we have our I0 still, okay? Because if you sub in your 1, 2n minus 2 is 0, okay? When n equals to 1, your 2, oh, sorry, I mean when your n equals to 0, okay? When your n equals to 0, so you get 2 times 0 over 2 times 0 plus 1, but you have 0 on the top, so you just get 0. So in this case, we can't do it. We don't have, we can't derive for an in minus 1, okay? So all we're left with is just I0. All right, so next thing, figure out what I0 is important. So I get integrate 0 pi on 2 sine 2 0 plus 1 2 theta times d theta. That's from my memory. And then I would get integrate 0 pi on 2 sine 2 theta times d theta. So what I get is negative half. Integrate sine, you get negative cos, so negative cos 2 theta, right? And then over here, this whole thing is going to go from 0 to pi on 2. So you can take the negative and negative and the half out. So what you get is just half cos 2 theta, 0 to pi on 2. So you get half cos 2 times pi on 2. That's just cos pi. Cos pi is negative 1. And then minus cos 0. 2 times 0 is 0. So 1 minus 1. 1 minus 1. Okay, I'll write the 1 on top. So which is half times oh, sorry. I already draw the negative out. I already draw the negative half out. So inside it will just be positive. So I get negative half, negative half, negative half. Now we get negative 2 here. And what we should get is just 1. Okay, just a single digit 1. We know that I0 is equal to 1. Yeah. All right, so I know that I0 is 1. So essentially I just have my 2n. What you can do is 2n, 2n minus 2, 2n minus 4, dot, 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 and all the way on for 2. We'll rub this out. Let's wrap it up. Over 2n plus 1. And all your even numbers, 2n minus 1, 2n minus 3, 2n minus 5, and dot, dot, dot to your 3. Okay, let's again look at it. We see a complete factorial down the bottom, okay? If it's a factorial, that means we're going to have from 2n plus 1 times 2n times 2n minus 1 and so on. And you can see we are missing the even numbers, okay? We're missing basically our numerators. What you now should do is very easy, times by your numerator over your numerator again. So 2n, 2n minus 2, 2n minus 4, all the way to 2 over 2n plus 1, 2n sorry. What am I writing? It's getting a bit late. So 2n, 2n minus 2, 2n minus 4, and so on, right? Essentially, we're times them by 1. And what we get is on the top, I'm going to do something special. What I get is 2 to the power of n for your first bit, okay? For your first bit, I get 2 to the power of n with n minus 1, n minus 2, and so on. You will see when I factorize the 2 out, that's what I get, and 1. So essentially, I'll get the same thing again as my 2 to the power of n times n minus 1, all the way till my 1. Which means I'll get my n factorial in this case. And then over, what I have is 2n plus 1 Now, because they're timesing each other, I can move the 2n forward. So 2n minus 1, 2n minus 2, and then 2n minus 3, and so on until my 3 times 2. And if you want, put that times 1 in the end if it really bothers you in making that full factorial. Okay. At this step, I think is very clear. What we get on the top is 2 to the power of n times n factorial, right, in my first. And now I also get another 2 to the power of n and n factorial on my second square bracket. On the bottom, I just get 2n plus 1 factorial. Okay. Now, last step of simplifying, 2 to the power of n times 2 to the power of n. I get 2 to the power of n plus n, and n factorial just squared over 2n plus 1 factorial. So 2 to the power of 2n, n factorial squared over 2n plus 1. Now, let's look at the next part. Next part, suddenly we do have a change of view. It says, let Jn equals to integrate 0, 1, x to the power of n, y minus x, to the power of n dx, n equals to 0, 1, 2. And now it says part 3, use the result of part 2, or otherwise show that Jn is equal to n factorial squared over 2n plus 1 factorial. Okay. This means we're going to do our substitution. So part 3. Let me copy the part 3 down. So part 3, it says Jn is equal to integrate 0, 1 xn 1 minus xn times dx. And we need to prove that Jn is n factorial squared over 2n plus 1 factorial. Okay. Now, this will be a relatively simple substitution. You will be using your sine 2 theta, okay? All you will be needing is your sine theta. What I mean is let x equals to sine squared theta, okay? Dx will be equal to 2 sine theta cos theta times d theta. Okay. Now, don't forget, you also need to replace your boundaries. So when x equals to 1, your theta is equal to square root of 1. So I assume that's, so just sine inverse 1, which means you're going to get pi on 2. When x equals to 0, your theta is just going to get to 0. I think everyone understands this step. Now, what we have is my Jn is going to equal to integrate from 0 to pi on 2 sine square theta to the power of n, 1 minus sine square theta to the power of n, and then changing my dx into my d theta times 2 sine theta cos theta times d theta. Okay? And what I will get is integrate 0 pi on 2, simplifying it further, sine 2n theta cos 2n theta times 2 sine theta cos theta times d theta. And simplifying one more, what I get is integrate 0 pi on 2 sine 2n plus 1 theta cos 2n plus 1 theta with the 2 at the front, okay, times d theta. How many of the sine 2 thetas we're going to make? We're going to make 2n plus 1 sine 2 thetas, okay? So what we will have is pull out that 2 and pull out a 2n plus 1, integrate 0 pi on 2 sine 2 theta, but 2n plus 1 times d theta, okay? Now I'm making my sine 2 thetas. And you can see at this point, this is just my in, okay? And on the front, this is 2n plus 1, okay? So on the front, I have my 2, and I'm going to cancel out the top and bottom. So what we'll get is 1 over 2 to the power of 2n. And we already proved what my in is equal to, okay? Maybe I'll write this, I'll continue this on the right. So what I get is equal to 1 on 2 to the power of 2n, integrate, well, don't need my integrate sign over here, my in, And I have proved that my in is essentially equals to 2 to the power of 2n, n factorial squared over 2n plus 1 factorial. Okay, 2 to the power of 2n and 2 to the power of cross out, and I know my jn is essentially just equal to n factorial squared over 2n plus 1 factorial. 2 to the power of n factorial squared less equal to 2n plus 1 factorial. Okay, what we need to use here is actually not from like part 1 or part 2. Well, we will need to use it, but essentially what we will be using is our jn function. Okay, the jn function over here is what we'll be need to using. Let's simplify our jn function a bit. So we know that jn is equal to integrate 0, 1, but now I'm going to pull out, oh sorry, it's wrong. I'm going to pull out that to the power of n, okay? So what I will get is x, 1 minus x to the power of n times dx. I'll get this whole thing, okay? Essentially, we're looking at a quadratic and raising to the power of n. So what we can figure out is the maximum value of the quadratic, okay? If you want, you can graph it as well. So, well, or you can expand it. So let's just talk about, I don't know if I'm going to have enough space, but I'm just going to write on the PDF. So what we have is x 1 minus x. And if you want to expand it, what we get is x minus x squared, okay? Using your axis of symmetry, or basically using how to find your vertex, what we have is the symmetry line will be x equals to negative b on 2a. I don't know how many of you guys remember this. So negative b on 2a. So remember, you have ax squared plus bx plus c. Okay. So what I have is negative 1 over 2 times negative 1. So what I get is a half. That is my vertex x value. And then I'll have my y value. My y will be equal to, subbing that in, half, 1 minus a half. I get half times a half, which is 1 on 4. And this will be my maximum value. How do I know this? Because it is a negative parabola, okay? I have 0 and 1, okay? At half, it is my vertex, or in a way, my maximum value, okay? So, which is 1 on 4 over here, max value. Okay, this is telling me that my Jn is equal to integrate 0, 1, x 1 minus x to the power of n times dx, and it will always be less than or equal to, integrate from 0 to 1, my 1 on 4 to the power of n, okay? Because 1 on 4 is the largest y value that it will get, times dx. Okay, so essentially I will have my right-hand side. I'm going to integrate this, so I get 1 on 4 to the power of n. Well, with an x, and then obviously we'll get 0 and 1. So essentially that's just 1 on 4 to the power of n, okay? And let's put our jn on the left-hand side. Our jn, as we defined, is, where is it? Yep, n factorial squared over 2n plus 1 factorial, okay? We know it's less, maybe I'll put less equal than sign again, less equal than. So n factorial squared over 2 n plus, why did I write the bracket inside? So 2n plus 1 factorial is less equal than, I now need to modify my 1 on 4n. So what I get is 1 over 2 n 2n, and which is usually you would write equal sign, so 1 on 2n. Okay, that's what I get. And if you don't see it from this step already, then I guess it's like similar to exam condition, okay? Then you're a bit stressed out, but all you need to do is cross multiply. So what I get is 2 to the power of 2n n factorial squared is less equal than, multiply this on the right hand side, I get 2n plus 1 factorial. Okay? Last thing is what we need to do is pull out that squared. So 2 to the power of n factorial. This whole thing squared is less than 2n plus 1 factorial. Okay?